arcs earlier in, we did regular areas and circles and things like that. We dealt with arcs and arc measures and all. We actually talked about things called chords. We revisited some of these terms over the past couple of days. For example, one of the things that I want you guys to remember is that a chord is a segment in a circle that has the endpoint on the circle. That's nothing new. We've defined it a few different times. We've used it in many occasions. The one chord that we have used over and over and over and over again has been a diameter. Now, remember, a diameter, chord is the segment with endpoints on the circle. Okay? And obviously a diameter has endpoints on the circle, so bless you. It winds up just becoming the fanciest chord that you can have. One of the things that also remember when we're dealing with this thing called a chord is a segment, so you got your endpoints. But what's different, the difference between chords and arcs. Okay? Chords are the segment. The arc is what they run into. Okay? Remember, we dealt with that thing called before. We called it an intersected arc. That was one of the terms we had used probably about 2-3 weeks ago or something along those lines. So chords intercept arcs. Chords are shorter than arcs, which means we have to remember a little thing about arc length. That part comes back as well. Now, remember, you've had the formulas for arc length. You've had all these formulas for all that stuff as well. Chords is just going to be some sort of numerical distance. An arc length, though, just a refresher here, was that angle over 360 times the circumference, 2 pi r. So you get a lot of little, I said this yesterday, as you get into circles, you'll start to see that the more I read about what they do in this chapter in the newer textbook versus what we've done in the past, it kind of makes sense of why they put it at the end, because you can do just about every section that we've seen so far, almost the whole year. You can relate it to something that you will use in this chapter. So it makes a little bit of sense of why they threw it at the end. So you get these things with the arcs, chords, and all that. The other thing that shows up looks like one of the problems you had yesterday. Remember yesterday, I think it was 15, I gave you guys that example, where you had a triangle that got created, and those other legs of the triangle happen to become radii, which meant that it created a what? Yeah, it created the isosceles triangles. So what will happen here a lot of times, again, you'll see that you'll get isosceles triangles. Remember, we dealt with this thing called arcs and angles. This angle here is the same measure as this arc. So if this angle measured 100 degrees, this arc measured 100 degrees. If that angle measured 100 degrees, what was the angle at D and what was the angle at C? Good, they're both 40 because it becomes isosceles. So that means, bless you, those two base angles would be the same. It's that little subtlety of things that you guys have done before. It's just kind of all bringing it into one section. Believe me, the math here today is much easier than what we were doing yesterday with the tangent stuff, with the Pythagorean theorems, and well, I should say, you might see a couple of those, but there's not as much, it's hard to throw a factoring probably with one of these things. What else was there on this? The other thing that happens a lot, excuse me, the other thing that happens a lot with chords is that we're going to talk about them in terms of relationships between one another. Do you guys all agree that if you're in a circle, one circle, that the radius always stays the same? Which means the diameter would be twice the radius. Is there any segment when you're in a circle that could be larger than a diameter? No, because remember, if you have a diameter, it goes through the center of the circle. It has to be the largest segment because as soon as it starts moving off, its endpoints are no longer in the circle; they're outside the circle. So that's one of those little concept things. It makes sense, but unless you start really thinking about it, it's one of those weird things that happen. Let's see. Yeah, those are first definitions. The other thing that shows up here are, you've defined these before as well, major and minor arcs. They come in as far as describing something in a diagram. We'll say, ABC is a major arc, and you'll have to remember what that meant. Now, again, we defined this thing a couple of weeks ago, so it might have been a while, but what made a major arc versus a minor arc? What was the difference between the two? Yes, sir. You're close. You're close. You can have a minor arc that's larger than 90. It's larger than 80. Okay. When you get into a circle, you're thinking obtuse and acute. When you get to a circle, you have to add the extra degrees to it. Okay. So the major arc were the arcs that were greater than 180. The minor arc was less than 180. What was the arc called if it equaled 180? Remember that? What's that? The arc. The arc. The segment. Cool. What are you saying, Maddie? What? Oh, I thought you said something else. Sorry, when you were saying something, I thought you had said something else. But not the central angle. I know you're like the measure of an arc is the measure of the central angle. So what happens if what is the arc called if it equals 180 degrees? You're gonna kick yourself. Well, probably more like literally or figuratively. Or turn it off. Remember this thing called a semicircle? Yeah. No. If it equaled 180, it was a semicircle. Again, when you're dealing with arcs, it's dependent upon letters. Bless you. We did this, we described the difference generally between major and minor. How many letters did you use for major? 3. Yeah, we used 3. And for minor, it was usually 2. The reason why we would say 3 letters, if I look at arc AD, if I just say arc AD, that meant I'm going shortest distance between A to D. But if I say arc ACD, that means I have to go A to D, but I have to pass through C to get there. That's why we use 3 letters. Don't get me wrong, sometimes you might use 3 letters for a minor arc, but it's not as common. I mean, I could probably say that BCD would be a minor arc, but usually you don't need to use 3 letters for that. This guy had 3 letters, so usually 2. Pretty sure semicircles were either 1. If you remember, sometimes in directions of things, it always said segments that appear to be diameters are. Remember reading that a few times? That still shows up like that. So if you see a diameter, you know you got a semicircle. I just wanted to throw a quick little refresher here on a few of these before I get going too far in here. But I'm guessing so far so good. Yay. Okay. Now, always one. She's so smug about it too. This is where it starts getting kind of weird. When you have circles, in order to have congruent circles are going to be circles that have the same radius. Okay? If circles have the same radius, they're always congruent. or you're inside the same circle. And when you're in the same circle, you're always congruent to yourself, so that's not a big deal. What happens here is that if two arcs are congruent, if and only if their chords are congruent. And that means the same thing. Two chords are congruent if and only if their arcs are congruent. And it sounds really, really weird for something that's pretty easy to show why it works. For example, let's see, if I look at a circle, imagine that it's pristinely drawn and looks awesome. Not like junk. Those are what? Yes, ma'am. They're congruent, but what are they called in the circle? Radius. Okay. So you've got two radii. All right. Now, let's say, for example, that this is 80 degrees. You guys are okay knowing that if that's 80 degrees, these two base angles have to be how much? 50. Everybody okay with that? That means this arc is how much? 80 degrees. Good. It means that arc would have 80 degrees. I'm not worried about arc length as of right now, because I'm not giving a specific value for the radius. Now, if I draw in another one of these, I call that 80 degrees. What are these two base angles? 50. Are those two triangles congruent to each other? Why? Which one? Which reason? Oops. Sorry, I wasn't here yet. Which reason? Do you remember the reasons we did that first semester? Think of the alphabet soup. Think of the alphabet soup. Remember all the different ways you can prove triangles being congruent? Which one? Yeah, which ones? Everybody see that? What happens here is you get side, angle, side. Side, angle, side. We know the radii are always congruent, so right there, there's all my sets of sides. I know that I said that I have two 80-degree angles. They don't necessarily have to be vertical to one another. As long as I say it's 80 degrees, it's got to be congruent. Do you guys agree on that? So if I say that these two triangles are by side, angle, side, what do I know about these two parts? They have to also be congruent because remember that whole, all those letters of, remember all that? The idea that the reason why all of this stuff works and it comes together is because over the course of the school year, we've been slowly adding to all these different reasons of why certain things happen naturally in math. And one of the things we talked about was this thing called side, angle, side. When you have two sides and an included angle, that means the triangles themselves are congruent. When you have two congruent triangles, then all the corresponding parts are congruent. That's why those two separate chords would be the same. And again, since those two chords are the same, that means that our two central angles are the same, which means that our two intercepted arcs are the same. It's why all of this stuff comes back and around to why it works. Whether that's in one circle, or if I draw it up into two of them. Because it will always, always, always have to work. Okay? Same idea. If I drew these in as radii, here and here, here and here, they all have to be the same. These central angles have to be the same. So you get side on side, which means these have to be the same, which means this is the same. And if you go in reverse, if you start with your arcs being the same, that means your chord has to be the same, which means that they have to be connected to radii which are the same. You can go on and on and on backwards that way. Math is weird why everything works. It just maths like that. But yeah, like I said, It's not that it's horribly weird, difficult, crazy. It's just encompassing so much stuff that you've done to show why it works. Not that you have to do any proof here. Don't worry about that. I'm just saying where it comes from. Which lets you to do stuff like this. Again, if you have very simple math here, if I have, well, let me ask you this. Are those two chords congruent? Are those two chords in the same circle? Yeah, those two chords are in the same circle, which means that if I draw in the radii going to both edges, that happens, correct? Does that mean that the triangles are the same? Does that mean that the central angles are the same? Which means if this one, if GH is 100, that angle here is 100, which makes this angle 100, which makes this 100. It goes back and forth just like that because of the relationship to all the pieces. Right. Again, it's not crazy math. It's just recognizing that if you're in the same circle and the chord itself is the same, that chord will automatically intercept the exact same amount of either part of the circle. I showed this with a couple of rulers in the second hour. For example, do you guys agree that these are two pencils?
Yeah.
Are either of these pencils sharpened?
No.
Is there nothing up my sleeves? I swear there's nothing up my sleeves. Same idea. If I place this one here, oops, let's see how this will work. And I place this one here. Don't you join in? If I place that there and here, they're going to automatically intercept the same amount of the circle. No matter where this goes, as long as those endpoints are on that circle, they're always going to run in the same amount. Just because they're the same length. They're Yeah, exactly. That's a good way of looking at it. If you have a, sorry, this all of a sudden looks like a bowling ball. If you take a circle, you guys heard of the word inscribe? We did this before when we did the hexagon. We put a hexagon inside of a circle. If you inscribe a square inside of a circle, since each part of the square is the same, that makes each of the arcs the same. So if this is a square, what does it make each of those arcs? 90. So each arc here becomes 90 degrees. All right. I'm actually glad you brought up the square. When I draw the diagonal of a square, what is that of the circle? Diameter. Good. So the diameter then creates a semicircle, doesn't it? All right. Now, watch this. Do you guys agree that this angle is on the circle? Now, that angle moves out from here to here. How many degrees did that angle run into on the circle? How many degrees is the arc that it ran into? 180. What's the measure of the angle, though? 90. Okay. When we did let's see if I can get this to work. We did a circle, when we did the hexagon. Do you guys remember how many degrees each base angle was from a hexagon? That's the outside, so the inside would be, that's the outside, so the inside would be 120. So if each of these were 120, I know where you're getting with here. All of these on the outside are how much? Those are the 60s. Now, if I pick this angle here, how many degrees did that run into? Well, it ran into 1, 2, 3, 4 60-degree arcs, which is how much? 240, isn't it? What's half of 240? Isn't that the angle here? We'll do that stuff tomorrow. That's the other relationship between angles and the arcs as we get into tomorrow. But that when you said square, I'm like, all right, let me show you guys that real quick. So, the other thing that happens, which is also super easy to see, is that if you have a diameter, since the diameter is the largest chord inside of a circle, if you have a diameter and the diameter is perpendicular to another chord, that other chord will automatically be bisected. Or you can say another way. If two chords, I'm sorry, if one chord is the perpendicular bisector of another, then one of them has to be a diameter. Or if the diameter is perpendicular to a chord, it bisects the chord. It's kind of a weird way of showing that no matter where you put, or no matter how you draw it, since you have a circle, when you have a chord going through the circle, since the chord, since the diameter, if it's going to be perpendicular to it and bisecting it, that means it has to go through the center of the circle. Otherwise, if it didn't, it wouldn't be a diameter. If it didn't measure 90 degrees, it wouldn't be perpendicular, and therefore it wouldn't bisect it. And it's because the fact that this diameter is the longest segment inside of a circle. So no matter what, the diameter will always be, excuse me, if the diameter can be drawn to become the perpendicular bisector of a chord. Just real quick, when I look at that, I see that I now have what kind of an angle shown. We have that 90-degree angle right there, don't we? When you had 90-degree angles, yeah, or 90-degree angles. When you had 90-degree angles, one of the things that we always wound up having to use was Pythagorean theorem. Oh, super excited! Yay! You did Pythagorean theorem. You could have done SOHCAHTOA. There's so many different things that show up when you have right triangles. Because the very second I do this, I create right triangles. I create congruent right triangles. There's a lot of information that you're going to be able to do from this just by some very, very simple, easy math. Right? So again, don't freak out when you see all these complex pictures, because nothing in any of these pictures is going to be anything different than something you have seen at some point in time in this class. It's just putting it all into one diagram. Right. Yeah. Yeah. Same thing goes for this one. If two chords are equidistant to the center, then those chords have to be congruent. All right? If two chords are congruent, then the two chords are equidistant to the center. Now, when we did that here in this crazy diagram, we didn't draw it as equidistant. We drew it via the radii. Now, if I draw equidistant to the center, we're always drawing perpendicular distance. So if I do that, I'm drawing perpendicular distance, which means if I'm perpendicular to a chord, I bisect the chord, which creates side angle side over and over, or excuse me, hypotenuse leg with this stuff, which gives you these distances being the same. Again, it's a lot of special right triangles. Congruent right triangles and congruent triangles of the relationships of why these things can go back and forth between all And when we get to the math portion of it, it's super easy. It's just one of those things you'll see. Oh, okay. So again, if two chords are congruent, they have to be equidistant. If two chords are equidistant, then they have to be congruent. Because if they weren't the same distance, then they wouldn't have the same arcs. If they didn't have the same arcs, then they wouldn't have the same radii. If they didn't have the same radii, they wouldn't have the same angles, which would be the same arcs, and so on. It nickels and dimes, yeah. For example, find the given measure. Why? That's like rough sketch. It's always can be this whole thing of subject to change. Whatever. I don't know how well you can see this, but we're solving for x in this one. But obviously, if you had this in front of you, it would be a little bit easier to notice that these guys are perpendicular, and there's tick marks here to show that they are the same distance, which means what do you have to know about those two chords? They have to be equal. So you have to do a quick little algebra. Now, normally I would say pick on the little guy, but in this case, if I picked on the little guy, then I'd have to get a 0, then I'd have to add the other one. So just to save a step, I'm going to actually pick on the big person this time. So I'm going to subtract the 35. So if I subtract the 35x, does this value of negative 16 automatically become positive? Nope, there's still a negative there, so you just rewrite. And then what would x have to equal? Excuse me. Okay. From that, I could also ask you, what does the arc xz equal? I can make you take the extra step. If I ask you what arc xz is, what would you do with that value of 4? Yep, that's substitute in for x. So what do you get when you multiply 31 times 4? Okay. And since these guys are the same, I was wondering, I wasn't sure where you got that 112 right off the top of your head. I was, because I was about to say, I would double check to make sure that you didn't screw something up. I know. You kill me. And as Miss Epps is so eloquently, stottily provided for us, if that's a word. She just took the 2 of them and subtracted them from the 360 because that's how many degrees in a circle. Then you got, what was it, 112? Again, this really isn't all that terrible. That one, we'll do a second one here real quick. Oh, no. Try one more. Just solve for x. Solve for x on that one for me. I'll get you some numbers. I agree. You guys all get one? Okay. I walk past you.
Only solve for x?
This one says, yeah, this one's just solve for x. So when you're doing these, remember the math of this really isn't all that tough. It's the idea of identifying what kind of a setup do you have. Are you dealing with segments? Are you dealing with arcs? Or is it asking you to find a radius? Is it asking you to take something and go an extra step? Here it said just solve for x, which meant since these two guys are equidistant and perpendicular, that meant they have to be equal. Subtract the 4x, add the 5, we get what? 2x is 18, x is 9. All right. Get through that page. It looks like there's a lot. I don't think it should take any more than 10, 15 minutes. I really don't. The math part on it is really, really, really quick. Okay? The whole thing, yeah, it shouldn't take very long. It's pretty quick on it. Yes, sir.
How many passes? You gonna die?
What do you got, Josie? Yes, please.
You guys could have also gone to class. Let you see what. Take this one here, I guess, if you really want to get along. Yes. Where's your proof? What a snake guy.
Sometimes people are just. I've done